This is the Further Maths Support Programme Wales Year 11 to Year 12 Bridging course on differential calculus. Now, calculus is a major area of mathematics and it underpins the A-level course in Year 12 and in Year 13. If you continue and study any type of mathematics-based degree, you will more than likely be seeing calculus again. Today we're going to focus on one branch. There's two branches, being differentiation, and in a few sessions time from now we'll also look at integration. In this session I'm going to look at four different parts. First, I'm going to actually show you how to what we call differentiate an algebraic expression, the level what we need to know for the Year 12 AS course. Once we've learned that skill, we're then going to look at how to work out the equation of a tangent to a curve. So what is the actual equation of any line that touches a curve at a certain point? In part 3, we're going to look at actually working out where the maxima and minima are of curves. These are the peaks and troughs if you're going along a curve. For example, in y equals x squared, you know that there is a trough at the bottom, don't you? That's a minimum, and we're actually going to work out where these are. And in the fourth part, I'm going to actually explain why this actually works. Why in part 1, differentiating expressions, you get the result that we do get, and we're going to do it from what we call first principles. Part 1, differentiating expressions. So first, let's set the scene of why we have differentiation. So in your GCSE course, you could have been asked to work out the gradient, i.e. the steepness of the curve at any point. So what would you be asked in GCSE? So for example, find an estimate for the gradient of the curve y equals x squared, which we have here, at the point x equals 1. So if I look at x equals 1, I go up to the curve, and I want to work out the gradient here. So what you would do is, with a ruler, you would draw a tangent, a line that touches it there and is approximately falls away from the curve at equal rates above and below it. Now obviously this is subjective, it depends on who you are. My line here might be slightly different in steepness to yours. But anyway, there it is, there's my line. So if I want to work out the gradient now, I work out 2 points on my line, coordinates on the line. I set up the right angle triangle, as you can see here, and we then, to work out the gradient, I substitute those coordinates, bearing in mind that, remember, the gradient is the number in front of the x term, the coefficient of x, in the y equals mx plus c equation. The gradient is substituting in the x and y values of each point into this formula to get an actual result, in my case, in my estimate, of 8/5, 1.6. Now again, let me repeat, this is only an estimate of the gradient of the curve at this point. Yours might be slightly different. It's not an accurate answer. So that's what we're trying to work out now. How can I actually work out what the actual precise gradient is of y equals x squared at this point? So what is the actual gradient of the curve y equals x squared at any point? Well, here this table x shows you what it is at integer values for the x coordinate. So here it is, x equals 0 to 4. We know that the y coordinate, if y equals x squared is the curve we want to sketch, is 0, 1 squared, 2 squared, 3 squared for 9, 4 squared for 16. Now interestingly, the gradient, this is the actual gradient now, at these points is basically double the x coordinate. So at x equals 1, whereas I got in my estimate 1.6, for my tangent, the actual true gradient at that point is 2. And you'll find that for y equals x squared, it is always double the x coordinate. And just already you can see right at x equals 0, the origin, we know that y equals x squared is at its bottom, it's at its trough, technically what we call the minimum. And there it is. You can see that the gradient there is actually 0 because there's no steepness there. So for y equals x squared, the gradient is simply double the x coordinate. So why is this? Okay, so we're going to find the gradient of the curve using differentiation. So given the curve y equals f of x, now f of x you've seen before in your GCSE course, specifically in transformation of graphs. So f of x is an algebraic expression in terms of x. The mathematical notation for the gradient is written as, and we say this as dy by dx. Okay, so specifically in year 12, all we need to know is how to differentiate any expression with powers of x. So if y is x to the power of n, n can be any number, positive or negative or a fraction, the first differential, and so we also say first derivative, and usually in the context of the gradient is, and here is the formula, so dy by dx is equal to n times x to the power of n minus 1. Sometimes you may see it in this different way, where here you're saying d by dx of y is equal to, and it's exactly the same, n times x to the power of n minus 1. So how do we interpret this? It's very simple. It's just multiply by the power, and then you take 1 away from the power. Now, specifically, just to look at certain ones, if I have, for example, the line y equals x, now you know what the line y equals x looks like. It's just a diagonal line that cuts through the origin, and it's at 45 degrees from the x-axis. So for every 1 unit you go across, you go 1 unit up. So we know without any of this differentiation, we know that the gradient is 1, but it still works. dy by dx is 1 because y is equal to x is the same as x to the power of 1. So I times by the power, I take 1 away from the power, so it becomes x to the 0, and anything to the power of 0 is 1. So you can see it actually works, the formula does work in this context as well. So y equals x, dy by dx is 1, and to be a bit more general, if I look at any line that cuts through the origin, for example y equals 7x, dy by dx in this case is 7, so you just basically drop the x, but it does follow the formulae in the table above. And also, if I look at any horizontal line, which is y is equal to a constant, so wherever the horizontal line cuts the y-axis at that number, well, we know already by sight that it's got no gradient, it's 0, but it does follow again the logic of the formula above, because if I look at, for example, y equals 3, that's the same as 3 times 1, and we know that 1 is x to the 0. So basically I can write y equals 3 as 3 times x to the power of 0. And as soon as I follow the formula above, I times by the power, well, the power is 0. So 0 times anything is 0, and therefore dy by dx is 0. So I can either do it by intuition, just looking at the graph, y equals 3, but it also follows the formula above. So just to take note of these specific examples as well. I just want to show you another notation in case you see it, either in a textbook or in a mark scheme. for in your own studies. But another way of writing the first differential is instead of saying y equals x to the n, if we say f of x is equal to x to the n, and you'll be seeing f of x functions a lot in your A-level course, then the notation is for the differential is f and then an apostrophe, a dash there, x. So, and we say f prime x, and then it's exactly the same way of doing it. So in case you see this, here it is. Okay, let's have a look at some examples. So we're going to differentiate these expressions. We're going to work out dy by dx. So in A, we've got y equals x to the 7. We times by 7 and then take 1 away from the power. So if I substitute any value of x into that, that will give me the gradient of that particular curve, x to the 7, at that point. Okay, B, if you've got two separate terms in an expression, we treat them separately. And again, as always, remember the sign before the term. So in part B, we have 6 3s are 18 times by the power, and then take 1 away from the power. And if you remember, I said if it's just a constant times x, the gradient becomes just the number itself. So there we are, there's that one. Maths is very logical. Same applies for negative powers as well. So times by the power minus 4x. Now this is a place where students can make just a silly mistake. We all know that minus 4 take away 1 is minus 5, but I do see often just carelessly it goes to minus 3. So just be careful with that. Quite a common mistake. And if it's just a number, so the plus 8 drops to 0. Fractional power, so I times by the third and then take 1 from a third gives me minus 2/3. So that's the power there. And just to combine it with a number in front of the expression, the term as well. So in this case, 12 times minus a quarter is minus 3, and then taking 1 away from the power gives me minus 5/4. Okay, here's a few for you to try. So if you don't want to see the answers first, please stop the recording now. Here are the answers. Okay, I now need to show you how to work out the second differential of an expression. We need to use this in part 3 when we start looking at stationary points. So to find d squared y by dx squared, as we say, for each of the following. So here are my expressions. So basically it just means we have to differentiate the expression twice over. So if I look at A, for example, so dy by dx is 7x to the 6, and then d squared y by dx squared is doing the same thing to the expression above. So 6 7s are 42, and then take away 1 from the power. So all it is just doing it twice over. So the second one again, and you see this is like the expressions from the previous page. So 18x to the 5 minus 5. If I differentiate again, you get, well, 5 18s are 90, take 1 away from the power, and now this minus 5 drops to 0. And C, again, doing it twice over, we get that expression. The fractions, times by a third, power goes to minus 2/3, but now I've got to work with that expression and differentiate again to get d squared y by dx squared. So a third times minus 2/3 is minus 2/9, and minus 2/3 take away a whole is minus 5/3. Note how I keep the powers as improper fractions. I don't change them to mixed numbers because knowing what the power means, it's far simpler to interpret what you have to do with whatever the value is for x. In this case, for the last one, it would be taking the cube root, raising it to the power of 5, and then reciprocating because it's a negative power. And then part E, there's another example for you to look at. Here again are a few for you to try. So if you don't want to see the answers straight away, please stop the recording now. And here are the answers. Now that we can work out the gradient of the curve at any point, we're going to use this to work out what the equation of the line is of the tangent, the line that touches the curve at any point. So here we are, we've got a curve, and we're going to work out what the equation of that red line is, the tangent to the curve at that particular point. So we know we're going to be given the equation of the curve, which will be an algebraic expression like before. So to work out the gradient of the curve, we differentiate. And then what we do is we put it into this new equation, which you haven't seen before. Well, not in the GCSE course, it's not a requisite there, which is y minus y1. So y is our variable, like in y equals mx plus c, and x is in the same way. It's what the coordinates could be. And then we've got the x1 and the y1, which is the actual fixed coordinate on the curve. Now, if you know a point on the line and you know its gradient, if you substitute it into either of these formulae, and they are the same thing if you look at it carefully, we tend to use the left-hand one more often. You can actually work out what the equation of the line is. So it is just a different form of y equals mx plus c. So it's a very useful one because you know a point, you know the gradient. Substituting it into that gives you the equation. So let's look at a specific example. So find the equation of the tangent to the curve at y equals 3x squared plus 6x minus 7 at the point on the curve where x equals 1. So we need to work out what the y coordinate is because we haven't been given that. So we substitute 1 into the expression 3x squared plus 6x minus 7, which in this case gives us 2. So our x1, y1, the point on the curve, which is the point where the tangent touches the curve, is 1, 2. We need to work out the gradient. So we differentiate. So dy by dx in this case is 6x, yeah, from the 3x squared part. Then the 6x, the x drops down to 6, and the minus 7 is now 0 for the gradient. So 6x plus 6 is the general gradient of any point on the curve. So at x equals 1, we simply substitute 1 into that expression, which gives us 12. So our gradient for the tangent at x equals 1 is 12. So now we just simply substitute those values in correctly into the equation of the tangent, which is y minus y1 equals m bracket x minus x1. Be careful. Again, common mistake I see is we read obviously from left to right. So 1, 2 is our x and y coordinate for the point, but it's the 2 we put in first for the y minus part. Yeah, so just be careful. Don't write 1, y minus 1, and then the x minus 2 there. It's the other way around. So just be careful there. And our m is 12. Now that is the equation of the line. That is enough to see what it is. It's not necessary to do any more, but just for completeness, I've rearranged it. So obviously expanding the brackets and making y the subject, we get the form you have seen before, which is the y equals mx plus c form. So there's our 12, as you can still see. And now because I've rearranged it, that minus 10 tells me where the line crosses the y-axis, so the y-intercept. So the initial equation tells me the gradient and a point on the line. In this form, we've got the gradient and the y-intercept. So they're one and the same thing, just rearranged. And again, occasionally, you may be asked in an exam to give it in the form of ax plus by plus c equals 0. So all I've done is just simply collected everything over to one side of the equal sign to fit the form that they've asked. Now, like I said, these two parts are not necessary. You only obviously do what you're asked in an exam, but the second, the y equals mx plus c part is obviously important because you now know where it crosses the y-axis, but you are occasionally asked the third part as well. So there is an example of what we've got to do. So let's try, you've got to try one yourself now. So here's a past exam question. Note how they're actually asking you to work out the gradient, the equation of a tangent on a cubic curve at x equals -1. So as before, answer will come shortly, so please stop the recording now. Here's the answer. So just be careful now, this is where negative numbers rear their ugly head, and you've got to be careful with your powers. So just take care with that. One further point to just raise in the equation of the tangent in the third box. Remember, the formula is y minus y1. So here again we've got and x minus x1, so we've got double negatives here. So you would have to change the double negatives and make them plus. So obviously we don't normally have two signs in an expression. So there it is. There's the actual equation of this line, and then rearranged again. In this example, I found they're actually testing your fractional power work as well. So as before, answers follow shortly. Stop the recording now, please. And here is the answer. Now in this example, they're actually asking you to work out the x-coordinate on the curve and when you're given the gradient. So there is an example. So we've got y equals x squared minus x, and we've got to work out what the x-coordinate is of the point on the curve when the tangent at that point is 3. So the first thing we've got to do is we differentiate the expression. So that becomes 2x minus 1. And then we've been told we've got to work out this x-coordinate when the gradient is 3. So we equate the expression to 3 and solve, and there it is. That is the x-coordinate. They could ask you to work out the y-coordinate, and then you would substitute that x equals 2 into the expression x squared minus x to give the y-coordinate. Here are 2 past exam questions for you to try. Answers follow shortly. Part 3, the stationary points of a curve, which are the maxima and the minima. So here is an example of a curve which has a maximum point and a minimum point. Collectively, they're called stationary points. And as you can see, with the tangents at the maximum and the minimum, the gradient is 0. and every maximum or minima will have this. So a maximum is your peak, a minimum is your trough, and in this part of the course, that is all you need to know. There are other types as well called inflection points, which you will look at in your A level. So we just focus on these two. So at any maxima or minimum, dy by dx is equal to naught. So if I actually had the x coordinate of these points and I substituted it into my differentiated expression, or which describes the curve, you will get 0 if it is at the maximum or the minimum. Now, how do we distinguish between the two? Because they both have a gradient of 0. Well, the way we distinguish and what they are called are the nature of the curve. So what is the nature? How do I determine what the nature is at a particular stationary point, whether it's a maximum or a minimum? What we do is we have to second differentiate the expression. So this is a skill that we learnt in the first part of this session. So we work out d squared y by dx squared, and then if I substitute in the same x coordinate of the maxima in this case, and I get a negative value, I know that it's a maximum. And the opposite to this is if I substitute the x coordinate into the second differential and I get a positive value, I know it's going to be a minimum. So take care here, because it is actually a bit counterintuitive. We always think of maximum meaning a high value or positive value, minimum being less or negative, but here it's the opposite. And the reason is just simply is d squared y by dx squared describes the rate of change of the gradient. And if you look at the gradient around the maximum point at point A, if you look just before it, it's got a positive gradient, and as you go round the curve, it hits the maximum point and then it's naught, and then the gradient after that gets more and more negative. So the rate of change of the gradient is decreasing, so it's going from a positive to a negative gradient, and that's why the second differential, the rate of change of the gradient, is negative. And again, the opposite to this is at a minimum point, just before the minimum point, it's got a negative gradient, then it's naught, and then after the minimum point, it increases more and more. So the rate of change of the gradient is increasing, which is why it's positive. Okay, so there we are. There's how to what the properties are of the maximum and minimum points. So let's have a look at an example on the sort of questions you will be asked. So here is a standard exam question where we're asked to find the coordinates of the stationary point on the curve y equals 3x squared plus 24x plus 7 and determine its nature. So the first thing we do is we differentiate and work out dy by dx. In this case, it's 6x plus 24. And to work out the x coordinates, firstly, well, we've been told to work out where this stationary point is. So we know that dy by dx is going to be 0. So we assign 6x plus 24, we equate it, to naught, solve that equation, and in this case we get x equals minus 4. And then to work out the y coordinate, we substitute this minus 4 into the original expression which describes the curve. So we substitute minus 4 in, and in this case we get minus 41 for the y coordinate. So there we are, there's the actual coordinate of the stationary point, minus 4, minus 41. So at the moment, all we know is that there is a stationary point at this coordinate, but we don't know its nature. We don't know if it's a maximum or a minimum. Now, if you've got any experience at drawing quadratic curves, you will already know that a positive x squared is going to give us a parabola, a U shape. So we know just from experience that it is a minimum as the stationary points. But that's not enough in mathematics. We actually have to prove this. So this is where we now work out d squared y by dx squared. So what we do is we've got our dy by dx already at the top, which is 6x plus 24, and it's this that we differentiate again. So we do so, and we get a actual value. We get 6 for this second differential. So that is not an expression. 6 is a number, and it is positive. And because it's positive, that immediately implies that this stationary point is a minimum, which we did actually know, but there is the proof. So there we are. There is an example of an exam question and how you would answer it. Okay, I have 2 examples of past exam questions. So as always, please have a go at them, and the answers will appear in due course, so please stop the recording now. Here are the answers. Right, here is another example where we've got to work out the stationary points and their nature, but in this case it's a cubic curve. Now again, if you've got any experience of drawing these, you will know that a cubic in general has 2 distinct stationary points, one being a maximum and one being a minimum. But again, we're going to work this out mathematically, where they are and what they are. And you can see from the question itself, it's actually asking for the nature of the stationary points. It's plural, not like before where it was asking for the stationary point. So it's exactly the same method. First thing we do is we differentiate the expression. And in this case, we get dy by dx to be equal to 6x squared minus 6. We then equate it to 0. But as you can see, in this case, we actually get a quadratic expression. So 6x squared minus 6 is equal to 0. Then from here, this is the method I would like you to see of how to solve this. Well, the first thing I'm going to do is simplify the coefficients, the numbers. So I can simplify that to x squared minus 1 equals 0. And then now that it's set to 0, I would prefer you to factorize the expression. As you can see here, this is the difference of 2 squares. So obviously you could have different brackets, double brackets here, but clearly this is difference of 2 squares, x plus 1, x minus 1, which therefore gives us a solution of x to be either 1 or minus 1. So I've got 2 different x values, and that is what we would expect because it is a cubic with 2 stationary points. So we've got to work out the y coordinates of each. So again, we substitute each of those numbers in, x coordinates, into the expression which describes the curve. So x being 1 gives y equal to 1. And if I substitute minus 1 in, you get 9 as the output, which is the y coordinate. Now, be careful. Those numbers are attached to each other. You can't mix them up. 1 gives 1 for the y, and minus 1 gives 9 for the y. And there they are. There are the 2 coordinates of the stationary points. But now we have to determine what their nature are. So that's the next step. So as before, to work out the nature, we have to work out d squared y by dx squared, which in this case is 12x. And then we substitute in the coordinates x equals 1 and x equals minus 1 into this second differential. So we get 12 times 1 is 12, which is clearly positive. Therefore, we now know that 1, 1 is a minimum. And substituting minus 1 into the expression gives minus 12 for the second differential, which is negative. Hence, minus 19 is a maximum. Okay, I've got two questions for you to try. So here's the first one. Again, if you don't want to see the answers straight away, stop the recording now. Here are the answers. And here is question 2. Stop the recording now. And the answers. Okay, so we're going to finish this session by looking at something called differentiation from first principles. So we're going to wrap up the session explaining why the differential of expressions is what they were. So with, for example, y equals x squared, why is it 2x? Now, when students first see this, they can be quite overwhelmed because we've certainly left GCSE maths behind now, and initially what you see is algebraically and conceptually a bit daunting. So you probably need to watch this part of this session more than once, but eventually it does make sense. You just have to work through it carefully. So we're going to look at the curve y equals x squared. So here it is. Here's part of y equals x squared in the first quadrant. And what we're going to do is we're going to draw a chord on this curve where points A and B are on the curve. Now A is just a general point on the curve with coordinates x, y. And then what we're going to do is the point B is slightly up on the curve or slightly along the curve, and this slight distance further along, represented on the x and the y coordinates, we're going to represent it by delta x and delta y. Now delta x, normally you would think, oh, this means delta times x, but in this case it just means a small amount along the x-axis on the curve, and in turn a small amount on the y-axis for the y-coordinate of the curve. So you've got to treat this as a separate letter, and it just means a small amount. Sometimes you will see h in a mark scheme as well, so they are interchangeable, but delta is a letter we use a lot, especially in what we call the theory of limits, and you will see this if you do mathematics at university especially. It's got a special usage. Delta is what we tend to use frequently. So there we are. We've gone up slightly along the x by delta x and up along the y by delta y. So if I want to work out the gradient of this chord, as before, we know that it's the difference of the y's divided by the difference of the x's. And if we substitute those particular values in for y2 minus y1 divided by x2 minus x1, we get the gradient to be delta y by delta x. And it always will be, no matter what the curve is that you start with, you will always end up with delta y by delta x as the gradient of the chord. So in this case, we're looking at y equals x squared. So what we do is we substitute, because we're looking at point B, we're going to substitute x plus delta x for the x term and y plus delta y for the y term, as you can see. So there's the structure y equals x squared in the first line. And then if I expand the double bracket there, we get the expression below. Now the brackets I've got wrapped around the delta x is purely there for you to see clearly that delta x is treated as a single letter, and it has no other mathematical meaning. You don't have to have it there. I'm purely writing it there for so you can see it clearly. So there we are. There it is. There's the expanded right hand side. But we know in this case that y does equal to x squared. So I can actually cancel down the y and the x squared from that line, as you can see there, and we are left with delta y is equal to 2x delta x plus delta x squared. Now, we're trying to aim for the gradient of this chord, which is delta y by delta x. So to make that the subject of this particular equation, the delta y by delta x, I've got to divide both sides by delta x, which is what I've done there. Now, the right-hand side now can be simplified because I've got two terms on the top. So the 2x delta x, if I divide by delta x, becomes 2x, and the delta x squared divided by delta x becomes just simply delta x. The power drops by 1. So there it is. That is the gradient of this chord from point A to B, where the 2 points are on the curve y equals x squared. So here is the clever part. From that line there, what we're going to do is we're going to now make delta x smaller and smaller. So what we're doing is point B is getting dragged down closer and closer to point A on the curve. And as it does so, the gradient of the chord approaches the gradient of the tangent. So B is being dragged down nearer and nearer to A. And eventually it does become A. And once the chord AB becomes so small that B is on A, the chord becomes a tangent at point A. And that is what is being described here mathematically in the red box. So what that is saying, if I read that, is saying dy by dx, which is the gradient, is equal to the limit as delta x tends to naught of delta y divided by delta x. So this line must be written, and what we're saying here mathematically is that point B is being dragged down all the way to A. So that delta x is getting nearer and nearer to naught. And if something gets nearer to naught, as you can see before, it was 2x plus delta x, that delta x disappears and you are left with 2x, which we know from part 1 is the actual gradient of the curve at any point on y equals x squared. So this is the new part. This is the conceptually takes a bit of time to think about, and this particular line is important when we actually prove the differential from first principles. So we're going to have a look at an example now and how to set it out. Here we go. We're going to work out the dy by dx from first principles of 3x squared minus 5. So immediately I'm just going to work it out in my head quickly. What should I get if I was going to do it quickly? And I know I'm going to get dy by dx is 6x. So I've got it in my head what I'm aiming for. So again, I replace y with y plus delta y and x with x plus delta x because I'm going slightly along the curve. And then there's the minus 5 there. And then I expand the double brackets, as you can see, which is what I've got there. But in this case, I've got that extra 3 as well. So I've got to multiply each of the terms in the bracket by 3, which is what I've got there. And then don't forget the minus 5 at the end. Then the next thing is I cancel out. Again, we know in this case that y does equal 3x squared minus 5. So I can actually subtract that equation from this one. And we are left with delta y is equal to 6x times delta x plus 3 times delta x all squared. Then the next step is I divide through by delta x both sides and I simplify the right hand side. So the delta x cancel from the first term and the power drops down by 1 on the second term, as you can see there. And then the final line, which has to be written accurately, is this. So dy by dx, this is the actual gradient, is equal to the limit of delta x tending to naught. Note it's a single line arrow, not double line, single line arrow, equal tending to naught of delta y divided by delta x. And again, because here any delta x term is essentially naught now, tending to naught, it disappears because 3 times naught obviously is naught. So it disappears and we are left with 6x. So if your first principle solution is set out like this, if I'm talking about exams, you will get full marks, and they're usually about 5 marks. So there it is. So I've got 2 examples for you, 2 questions for you to look at yourself. Okay, here's the first question of 2 I'd like you to try. Answers will follow now. There we are. Note how from line 3 to line 4, I can go from line 3 straight to line 4, so crossing out all the terms in the black, and then I can immediately go to delta y by delta x, just to save 1 line of work. You can go straight to that. And there's one more for you to look at. Here is a second question. And here are the answers, so please stop the video now. And there we are. That's the end of the session. Thank you. Diolch yn fawr.